So we finished pretty much with chapter 7. I think that was a real big thing that happened to us. So, well, we deserve to move to the chapter 8, right? How about that? So I'm gonna start a new story in chapter 8. Well, section 1 of it is an introductory little section that deals with triangle that has 90 degrees angle or a right triangle. And this right triangle is very similar to the one that we utilize to get our sine and cosine from. I guess word should be not very similar, but similar triangles. So if I have triangle on the unit circle produced by a point on the unit circle with coordinates xy, then x coordinate is going to be a cosine of this angle theta. So angle, I'd like to call it here as theta. And its y coordinate will be a sine of theta. He said, Alex, we already saw this so many times, so what is surprising here? Well, the fact that is not surprising, but be used heavily is that if you have triangle with a hypotenuse equal to the radius, or here they call it as a C, and sides such as a and a B with the same exact angle theta, and if that's also right triangle, just like the one we have here, because we're in rectangular system of coordinates, then this triangle will be called similar. And that's the keyword here. Oh, happy Halloween. Thank you so much. I hope everything stays safe this Halloween, but we'll see. So anyways, so theta is dealing with same angle in both triangles. And there is also, we have 1 for hypotenuse, and C is going to be a corresponding value on that triangle that doesn't have to be equal to 1. It can be any number. The only thing that is same will be angle theta, and the other angle 90 degrees. So the third angle in triangle is also the same then. And when 3 angles are the same, we say triangles are similar triangles. So what's so important about similar triangles? Well, the fact that corresponding angles give you corresponding sides give you same quotients. So maybe I can utilize here, let's say red, to tell them apart. And it turns out that if I divide, let's say C by 1, both hypotenuse, then this quotient is going to stay the same if I start to divide other corresponding sides. Like here, we have side, which is called sine of theta. And the other side here is called cosine of theta, right? X coordinate. So if I divide now sine and cosine into the corresponding sides to those on the bigger triangle, it doesn't have to be bigger, it could be smaller, and the corresponding side B to the sine and A to the cosine, then these quotients will be the same. And from here, I can use, let's say, first little identity to say that my value of A is equal to C times cosine of theta. And from the other one, saying that C over 1 is same as C, which is B over sine, I get that B is equal to C times sine theta. So notice I just took this little triangle, let's say, with a side cosine, and blew up that cosine hypotenuse number of times, because that's really coefficient at which we make this triangle bigger, and that's production of the other sides in any triangle. And this is really big pair of formulas, because you will see them throughout math courses from now and on. And it's nothing but similarity of triangles. I think it's good to realize this fact, because that way you will always be able to derive these formulas yourself if you forgot, because you will see them every once in a while. So what else here? Well, they use Pythagorean theorem for that bigger triangle, which is a squared plus b squared is equal to c squared. And that's actually another relationship in addition to this two that we can discover in here. And you could actually plug in those two and that Pythagorean theorem formula, those two, if you want to have some fun, and you will see that indeed it's c squared. So technically, Pythagorean theorem will derive from this two, which is interesting to know. But besides this, now they're gonna start to work with right triangle, and then they start working on it the following way. They produce these relationships between the angles and the sides, such as if you consider the big triangle here with hypotenuse C, then in order to find the sine of angle, sine of theta, what you do is just divide the opposite side. B is opposite to the angle theta, because angle theta is here. It's opposite. When you say, what if angle theta is here? Well, then B will be in the place of A. So it's still opposite side. That's so-called adjacent side, because it's touching my angle theta. And that is called as hypotenuse. And then we can produce various relationships, such as sine theta, which is B over C, or actually opposite over adjacent. And you can verify these, of course. I can write this down. Sine theta is going to be taking the opposite side divided by hypotenuse. Opposite over adjacent is tangent. So I derive this from the second little statement. Just try to divide by C both sides, you get B over C. So it's nothing else but hidden, and there's two last formulas that I told you they are big deal. They are really, even though they seem to be pretty straightforward, but for example, they give us all of these properties, such as cosine of theta is adjacent over hypotenuse. So these will be very good to remember, or to write it on the piece of paper. And that's coming out from the first one, because that's actually A over C. And We'll just look at the right triangle and we see A is adjacent, right? And C is hypotenuse, so I could just call them as adjacent and hypotenuse. And the third one I care about is tangent, right? And when I divide the sine by cosine, the C will cancel, so we're going to end up with B over A or opposite over adjacent. I just care about these three because if I know them, so the opposite is B and the adjacent is A. Because if I know them, then right away, sine reciprocal will be 1 over sine cosecant, so I flip that and get hypotenuse over opposite, and vice versa. So I guess you just reciprocate those, so you don't really need to remember the other three formulas in the second column. Just we should know that sine is 1 over cosecant, and cosine is a 1 over secant, and tangent is 1 over cotangent. So you reciprocate them, and that's about it. And this will be something that we're gonna utilize in this entire chapter. And they actually give you various little examples, and I guess I'm gonna just well, do my own problems because I'm sure you could read those examples. They're pretty good, and it never hurts to read those little examples, but I guess these be pretty much same as in the textbook. So I can just do these formulas, these problems. Again, we're in the chapter 8, finally, section 1. So let's try to get some of these exercises done, maybe like exercise 11. That says, what about if you have a triangle with sides 3 and 2, and angle theta here. 90 degrees angle is there. Please notice they do put this little box where 90 degrees angle is to make sure that you dealing with the right triangle. Because if they don't, well, you never know if this is right triangle, or maybe this is not 90 degrees, but 89.9 degrees, you see? So automatically nobody ever assumes that we have 90 degrees angle unless they tell you that, unless they put this little box. So then it's 90. That's important. So first of all, I can call these with letters, and for convenience, you don't have to, but just for convenience, we say that across our angle theta, like we had here, across was B. So I'm going to call this as B. So we just follow along this same formulas and don't get mixed up. And this is A. So first of all, I will find hypotenuse C, which is a square root from A squared plus B squared, right? Pythagorean theorem, we just saw it. So let's find this C, and it doesn't have to be a very nice number. So here we got 3 squared plus 2 squared. So we add 9 with 4, and that's 13. So it's square root 13. I don't want to use decimal. It'd be pretty annoying to get us some kind of number, like what is it, like 3 point something. So just keep square root 13, that so-called exact value, and that's, I guess, convenient. So they actually say here exact values. So that's what they want you to use. And now I'm going to find those sines and cosines and everything, because now we already have these 3 sides. So I take for the sine of theta B over C, and B is 2 and C is root 13. See, how do you know it? Well, it's given here. B is 2 and C is what we found, square root 13, etc. A is 3 over square root 13. And finally, tangent is 2/3. Well, they mentioned the other three, such as cosecant, secant, and cotangent. Well, I'll find them once, but I think it's kind of waste of time because all you have to do is recall the fact that they're reciprocals, right? So cosecant is reciprocal of sine. The secant is reciprocal of cosine. And cotangent is reciprocal of tangent. So I'm going to flip my values that I just produced. So if I flip sine, I get radical 13/2. I just flipped that guy. I flipped the other, I get radical 13/3. So you don't have to really pay attention to what the numbers are. They could be just some random results. You don't have to worry or panic when they look alike and try to make sense out of them. No, it's fine. You could just leave them as your answers. So the point of story that this group of exercises is all the same because there's nothing really hidden behind those. So I can do a problem from the next group. In fact, if you're doing the homework, I told you to do a couple of problems from this section, then all you need is just to, we just done 6 of these problems. So you can do a couple is good enough because you just keep doing the same thing. So if you find, say, sine and cosine, that's it. You can stop at that stage because that's already 2 little exercises because this exercise 11 consists of 6 questions. You found 6 functions. So how about problem number 19? What is this talking about? Well, there were formulas of so-called cofunctions, sine of pi over 2 minus theta, if you remember in the previous section, was cosine of theta. And vice versa, if you have cosine of pi over 2 minus theta, this was sine of theta. And if it was tangent, then it was changing with cotangent and so forth. So secant was cosecant pi over 2 minus theta. We utilize the sign of difference of two angles to show it, but you could also look at the right triangle and notice if theta is here and this is 90 degrees or pi over 2, then the other angle will be pi over 2 minus theta. Say, really? Why? Well, because the sum of 3 angles in any triangle is 180 degrees. Did you know that? 180 degrees. So whatever triangle you consider doesn't really matter. Right. And if you take angles, say alpha, beta, and gamma, the sum of all 3 angles will be 180. Or half rotation. If people like pi, you can call it as a pi. Same thing, 180 degrees. It's not hard to justify. You could just attach the line parallel to the base of this triangle and draw it through the third vertex. And then we can see that these 2 angles will be the same. So that's gamma. And these 2 are the same. You will see that fact if we have 2 parallels crossed by so-called transversal, that these 2 are the same. They called sometimes adjacent interior angles if you ever took geometry class. As well as this angle is the same, that's called vertical, but that's not what we care about right now. So two parallels, if this is alpha, then this is alpha. And you can see that these three angles now produce 180 or half rotation, alpha, beta, gamma. I guess that's a fact from geometry. So the point is, if I add theta with pi over 2 minus theta, plus minus theta will cancel. You get pi over 2, and this one is also pi over 2. So the whole thing, 180. So why am I so concerned with it? Well, because if I call this as a, just to be consistent, B was across theta, so this will be A, and this is C, then if I recall that, say, cosine of theta is adjacent over hypotenuse, then for the other angle, cosine will be that's opposite over hypotenuse. But that's with respect to this angle, opposite. And that's over sine. And it's the same yours. So let me see. So what are you trying to tell us now? Well, I'm trying to do exercise number 19 and tell that the result is going to be it's a sine of 38 that turns into cosine of 52. And when I subtract another cosine of 52 from it, I get 0. I say, Alex, I just used calculator and I got that. Yeah, technically you can do it, but they say do not use calculator. But I don't have control over this, what you're using or not, right? Because they're never gonna come to the campus for the test anyway, so you could technically use it. But I think it's fun thing, and in the next section, we're gonna utilize these ideas. So it turns out that these co-functions work with all the rest of these problems. You can try some of them on your own, same way, just write everything with A's and C's and you get the results. And I think that this is interesting. So I guess today's goal will be to start getting used to these formulas for any triangle whatsoever. And this is really powerful, I think, because we were stuck with only triangles that have hypotenuse equal to 1, right? That were on the unit circle, but now we're not just attached to the triangle that is coming from unit circle, but we deal with any triangle whatsoever. So let me do one more exercise, and that could be good enough here because there are not many problems in this section anyways. So I'll do one problem from the next group. So maybe I'll do 39, another recommended exercise here. So they have triangle, they clearly marked this sides such as a and B and 90 degrees angle, hypotenuse is C. Now here's one thing that is important to realize. We always call as angle A or vertex A, which is across to the side A. So that's standard. So across to side B will be called as a vertex B. And the third is C. So people say triangle ABC using its vertices is given. And sometimes they write it like that, triangle ABC. This meant to be triangle. Sometimes they refer to it like that in geometry. But anyways, let's try to see what's going on with 39. They gave us A equal to 5. So the point is always put it on the picture. Then everything will be in front of you and very clear. So I can find C right away. Square root from A squared plus B squared. I say, Alex, you didn't even read what they want. Yeah, it's a good idea to read what they want. They say solve triangle. What does that mean? Well, to solve triangle, you have to actually get all sides and all angles found. That's what's called solve triangle. So hypotenuse, I found right away. That's a square root from 5 squared plus 3 squared. So there'll be some number, which is 25 and 9. So this is a square root from 34. Okay, I can put it here for convenience. So I need to know the angles. How can I find those angles? Well, I already know that C is 90 degrees because it's a box here. So I just need to find one of these angles, A or B, and then subtract it from 180. So either way I can use. So for example, I can use my first formula. Doesn't matter which one you like to use. I can use first formula. So I can sine B is equal to B opposite over hypotenuse C, right? Or I could technically utilize these. So there are so many formulas. It's up to you which one you want to use. So now how can I get rid of sine if I need angle B? Well, people say apply arc sines on both sides because arc sine of a sine will kill each other and give me B. I say, but I remember it should be plus or minus. You made such a big deal out of this. Well, if it's a triangle, you don't have to worry about it because with triangle, angles are, at least with this one, less than 90 degrees. We can see it from the picture. It's a right triangle. So when it's 90 degrees, they all stay positive. So there is no issue with the main. So I just have to take arc cosine, arc sine of B over C. So instead of B, I put 3, instead of C is radical 34. And I will be able to get this value. Just make sure it's in the parentheses. And I'm going to use my favorite scientific calculator for that. So I'm going to start typing scientific calculator and choose it and use that Desmos, right? Choice 1. So remember where we used to get the arc sine from? Functions menu, right? Because it's not here. So you always go for functions menu, you find arc sine, then you go back to main menu where the numbers are and start entering your fractions. So it's 3 divided by square root 34. Now I want to keep it in degrees because with radians it'd be pretty difficult to pull out pi. So it's about 30 and something degrees. Not very nice number, 30.96. I say, Alex, can I round it approximately to 31? Yeah, why not? You can do that. I never pick on how people round unless they told to round some special way to hundreds or to thousands. But the convention says if sides given with whole numbers, then you can round up to next decimal. So this up to 0.2 or point something. So if I round this, I will get 31 approximately. And then to get A, you can use a cosine if you want, but what I will use is the fact that A is going to be 180 minus B and minus C. So in other words, it's from 90 subtract B, and when I subtract, it's going to be 59 degrees. Because their sum should be 90, right? As well as C is also 90, so the whole thing is 180. I guess this arc function use is going to be with us in this chapter all the time when we work with finding sides of triangles. So it's one specific. I think I should stop at this stage. It's going to be a little bit too much. I will continue. I will do another exercise of this type next time. And in the meantime, I will highly recommend that you try to look at this problem 39, especially. And I think 19 is not bad. So try to do them to your homework to do a couple of problems right from the section. So I would recommend those, but you can do whatever, especially in 39, because in the next sections, there'll be lots of exercises similar to 39. So you really want to get used to this process, and then you will see it again and again, and then you will start to feel more comfortable. And so that's why I don't give you a quiz today. I don't think it's time for it yet. You want to get used to this, finding this arc science, and that's the way to go. So I'm going to stop recording, and I'm gonna wish you happy Halloween and enjoy this trick-or-treating if you decide to try something like that. And if not, just have a great day and a good night.